Hello everyone. In this video we are going to discuss about chemical engineering GATE 2022 chemical reaction engineering questions with solution. GATE 2022 question paper and answer key link is available in my description box. You can download it. Question number 65. An elementary irreversible liquid phase reaction 2p gives Q. K is a rate constant, where the rate constant K 2 liter per mole minute takes place in an isothermal or constant temperature non-ideal reactor. The E curve in a tracer experiment is shown in the figure. Pure P is fed to the reactor. So pure P is fed to the reactor means that is a concentration 2 mole per liter Cp naught. Using the segregated model, the percentage conversion of P at the exit of the reactor is. Objective of this question is to determine the percentage conversion of P at the exit of the reactor is in terms of percentage. Xp. After calculating the percentage conversion of P value, we have to round off the result to the nearest integer. Refer this figure. In this figure, y-axis is a ET, minute power minus 1, x-axis is a time, t is minute. Data. 2p gives Q. This is given equation. K is a rate constant. K is a 2 liter per mole minute non-ideal reactor. So initial concentration Cp0 is equal to 2 mole per liter. So by using segregated model to determine the percentage conversion of P in terms of percentage. This is our objective. Solution: segregated model. Segregated model XA or X bar is equal to integral 0 to infinity to x of t into E of t into dt. So our reaction is a second order reaction. 2p gives Q. So x of t is equal to k into Ca0 into t by 1 plus k Ca0 into t. But our reactant is a P. So this equation can be written as x of t is equal to k into Cp0 into t by 1 plus k into Cp0 into t. So in this equation we know k value 2, Cp0 also 2. Substitute k on Cp0 value. X of t is equal to 2 into 2 into t divided by 1 plus 2 into 2 into t. So finally x of t is equal to 4t divided by 1 plus 4t. So this is a x of t value. Next we are going to concentrate the E of t. So area of E of t, that is 1. Okay. So area of the graph. Refer this graph or diagram. So here this is 0 to 1. The area of the E of t is equal to 1. So in this case we are going to find out the area of the E of t. This section is a two plane. One is a rectangle, another one is a triangle. So the addition of these two, that is equal to area of the E of t. So here this is the rectangle. So this rectangle section, area of the rectangle mean that is L into B. So here length and breadth. So here area of the rectangle, here you see 0.5 into 1. So the length is a 1, breadth is a 0.5, area rectangle area 0.5 into 1. Next triangle area. Triangle area of BH. So we want this section na. So we don't know what is the height. So this height we should take. So up to this, that is EM. So we should take, this is unknown, is right. So we don't know what is this value up to this EM. So up to this, so we know this is the 1. So what is this section up to this? So EM minus 1. Am I clear? So here EM minus 1. So already area of the rectangle L into B 0.5 into 1, that is 0.5. Area of the triangle half BH. We don't know the height value. So assume EM. So up to this we know 1A. So what is the rest of the things here? Em minus 1, this side. So now half BH. Half into B is up to this 0.5 base. Height is a Em minus 1. Substitute here. Half into 0.5 into Em minus 1. So now rectangle area 0.5 into 1, 0.5 plus half into 0.5 into Em minus 1, that is 0.5 into Em minus 0.25. So half into 0.5 na 0.25 into Em minus 0.25, that is equal to area of the E of t. Area of the E of t, refer this graph, that is 1. Okay, so from these Em values are 3. Okay, so up to this. So up to this Em value is equal to 3. Okay, this value equal to 3. Em is equal to 3. Am I clear? So up to 3 mean for rectangular section this is the 1. What about the height here? Em minus 1 means 3 minus 1, that is a 2. Okay. So here, so using the segregated model, so find out the E of t value here. E of t, so here, so we have 2 points is right up to this 0 to 0.5. So 0 to 0.5 here, point is a 0 comma 1, 0.5 comma 3. Refer this diagram here. This point. So first case 0 to 0.5. 0 to 0.5 mean this section. So here what is this point? This point. So what is this point? X axis is a 0, y axis is a 1, 0 comma 1. What is this point? This section? X axis is a 0.5, y axis is a 3, up to this 3 na. So 0.5 comma 3. Okay. So here point is a 0 to 0.5. So here x1 comma y1 0 comma 1, x2 comma y2 0.5 comma 3. Okay. So this is 0 comma 1, 0.5 comma 3. So x1 y1, this is x2 y2. So find out here et. So y minus y1 is equal to y2 minus y1 by x2 minus x1 into x minus x1. Here what is a y? Y is a y axis. Refer this diagram, that is et na. So y1 here 1 equal to y2 value 3, y1 value 1 divided by x2 value 0.5, x1 value 0 into x axis is a time t. x1 value is 0. Substitute all this value, et minus 1 is equal to 3 minus 1 2 by 0.5, that is 4, 4 into t 40. So from this et is equal to 40, this minus 1 comes to this side plus 1, 40 plus 1. Now come to the segregated model formula, that is x bar or xa is equal to integral 0 to infinity mean our limit is a 0 to 0.5. So x of t into e of t into dt. What is the x of t value here? X of t value 40 by 1 plus 40 na. This value x of t 40 by 1 plus 40. Take this value 40 by 1 plus 40. So into e of t here 40 plus 1 into dt. So the formula x bar or xa is equal to integral 0 to infinity to x of t into e of t into dt. So here any cancel, 40 plus 1, 40 plus 1 are cancelled. This is a common term na, this is cancel. Rest of the things 40 dt. So 4 is a constant, take outside. So the t integration t square by 2. Limit is a 0 to 0.5. So here 4 by 2 take outside. So upper limit is a 0.5 squared, lower limit is 0. Don't worry about the lower limit. Upper limit is a t squared mean 0.5 squared. So 0.5 squared into 4 by 2, that is 0.5. This is the x bar or xa conversion value or xp. So this is 50%. Answer for this question is conversion value 50%. Next question, question number 64. An elementary irreversible gas phase reaction A gives B plus C is carried out at fixed temperature and pressure in two separate ideal reactors. Two separate ideal reactor mean one is a plug flow reactor, another one is a CSTR. The first condition 10 meter cube plug flow reactor, that is PFR. Volume is a 10 meter cube. So another one 10 meter cube continuous steady tank reactor, that is CSTR. So both reactor volume is the same volume. If pure A is fed at 5 meter cube per hour to the PFR operating at 400 Kelvin, the conversion is 80%. So here capital A is fed to the PFR. Volumetric flow rate, that is V0, 5 meter cube per hour. Temperature 400 Kelvin. Conversion XA 80%. If a mixture 50 mole percentage of A and 50 mole percentage of on inert. So 50 mole percentage of A and 50 mole percent inert is fed at 5 meter cube per hour. This is volumetric flow rate to the CSTR. Operating at temperature 425 Kelvin. The conversion is 80%. We have two reactor, one is PFR, another one is a CSTR. So PFR condition is there, CSTR condition is there. So based upon these data, we are going to calculate the question. So the universal gas constant, capital R value, this is a constant value, 8.314 joule per mole Kelvin. Assumption is the Arrhenius rate law. Estimated activation energy is kilojoule per mole. Objective of this question to determine the activation energy. By using these two ideal reactors data, we are going to calculate the activation energy value. After calculating the activation energy value, we have to round off the result to 1 decimal place. Data. Given reaction A gives B plus C. So first one is a PFR, another one is a CSTR. Both are ideal reactors. Volume is equal to 10 meter cube. Volumetric flow rate is equal to 5 meter cube per hour. Temperature is equal to 400 Kelvin. Conversion is equal to 0.8. Gas constant 8.314 joule per mole Kelvin. For CSTR, volume is equal to 10 meter cube. 50 mole percentage of A and 50 mole percentage of inerts are fed to the reactor. Volumetric flow rate 5 meter cube per hour. Temperature 425 Kelvin. Conversion 0.8. Assumption Arrhenius rate law. Objective of this question to determine the activation energy in kilojoule per mole. Solution part, this is gas phase reaction. Gas phase reaction Ca is equal to Ca0 into 1 minus Xa by 1 plus epsilon A Xa. Our given reaction A gives B plus C. First one is a PFR. This is case 1. So a PFR equation tau is equal to Ca0 integral 0 to Xa dxa by minus Ra. So Ca0 integral 0 to Xa dxa by, so this is the first order reaction K into Ca minus Ra. What is a tau? Tau generally V by V0. So for this case, V is a 10 meter cube, V0 is a 5 meter cube per hour. This is a given data. So divided these two, tau values are 2. So take tau values are 2 is equal to Ca0 integral 0 to Xa. Here dxa is a numerator part. What is the denominator? K into Ca. So what is a Ca? Already this is gas phase reaction. Ca0 into 1 minus Xa by 1 plus epsilon A Xa. So what is epsilon here? Epsilon is a fractional conversion. Epsilon A formula stoichiometry of product minus stoichiometry of reactant divided by stoichiometry of reactant. So our equation is A gives B plus C. So epsilon A is equal to how many reactant, how many product here? Reactant is a 1, product is a 2. So B 1 mole, C 1 mole. So both are product now. So 1 plus 1, 2. This is a stoichiometry of product. Stoichiometry of reactant, we have only one reactant, that is 1. Whole divided by stoichiometry of reactant 1. 2 minus 1 by 1 is equal to 1. This is the fractional conversion. So here tau is equal to. So what is this? Tau is a 2 na. So this is 2 equal to Ca0. So here k inside, take outside. So Ca naught by k, integral 0 to xa, dxa by. So here Ca naught into 1 minus xa by 1 plus xa. So why? Because epsilon a values are 1. So 1 minus xa by 1 plus xa. Which one is a cancel here? Ca naught are cancelled. This is a common term. So after that 2 is equal to 1 by k, integral 0 to xa, 1 plus xa by 1 minus xa into dxa. So here 2 is equal to 1 by k, integral 0 to xa. So how will you solve this expression? So numerator part plus 1 minus 1. So value cannot change. So that's why 1 plus epsilon a plus 1 minus 1 divided by 1 minus xa into dxa. So by using this method to integrate this value. So 1 by k, integral 0 to xa, 1 plus 1, 2. Okay. So here rest of the things plus xa minus 1 na. Take minus outside. 1 minus xa whole divided by 1 minus xa into dxa. So separate the two section. One section is common term is a 1 by k, take outside. So one part is 0, integral 0 to xa, 2 by 1 minus xa into dxa. This is one part. Another part minus of 1 minus xa by 1 minus xa. 1 minus xa, 1 minus xa are cancelled. This is minus integral 0 to xa dxa. That's all. So the common term 1 by k integral. So here dxa by 1 minus xa. So dxa by 1 minus xa integration ln of minus ln of 1 minus xa. Here 2 is there, minus 2 into ln of 1 minus xa. Limit is 0 to xa. Minus dxa integration xa. Limit is 0 to xa. So here LHS side 1 2 is there. So RHS side 1 by k into minus 2 ln of 1 minus xa. How it is come this value? So don't worry about the lower limit. Substitute only upper limit. Minus 2 ln of 1 minus xa, upper limit. Lower limit means 0, ln 1 0. Don't worry about the lower limit. Minus this section, upper limit only take xa, lower limit 0, don't worry. So next one 2 is equal to 1 by k into minus 2 ln of, what is the xa value here? Xa is a given value 0.8, substitute here. 1 minus 0.8 minus 0.8. So 2 is equal to 1 by k minus 2 into ln of 1 minus 0.8 ln 0.2. That is minus 1.609 in minus 0.8. Finally we get k is equal to 1.209. So this k values are PFR. Okay, this is K1. K1 is equal to 1.209 first reactor. Second reactor is a MFR. So here this is the MFR na. So this section tau is equal to V by V naught is equal to Ca naught into Xa by minus Ra. So in this section tau is equal to V by V naught values are given. Take V and V naught value. V is a 10, V naught is a 5. So that is equal to 2. So here tau is equal to Ca naught into Xa by minus Ra mean K into Ca. Why? Because our equation is A gives B plus C na. So here we should take, that is minus Ra. Minus Ra is K into Ca. Okay, this is a first order reaction. So the Ca naught into Xa divided by, this is gas phase reaction na, K into, what is a Ca here? Ca naught into 1 minus Xa by 1 plus epsilon A Xa. This is gas phase reaction. So for this section tau values are to substitute. Here Ca naught are cancelled. What is the rest of the term? Xa divided by K into 1 minus Xa by 1 plus epsilon A Xa goes to numerator part. That is why 1 plus epsilon A into Xa is a numerator side. So we want epsilon A value. How will you calculate the epsilon A here? So in this section 50% of A, 50% of units are fed to the reactor. So we should take units value. So fractional conversion formula, stoichiometry of the product minus stoichiometry of the reactant divided by stoichiometry of the reactant into Y. So why take this Y value? Why? Because 50% of units are also fed to the reactor. That's why we should take Y value. Stoichiometry of the product mean we have the two product, already I said B, 1 mole of B, 1 mole of C, totally 2. Stoichiometry of the reactant, we have only one reactant, that is 1. 2 minus 1 divided by 1 into, so here this is the y value na, y is a 50% of inner surface to the reactor. So that's why 0.5. So 2 minus 1 by 1 into 0.5. This is equal to 0.5. Epsilon A values are 0.5. So see this expression, 2 is equal to numerator part 1 plus epsilon A is a 0.5, XA is a 0.8 into XA 0.8. XA's are given. Refer this problem, 80% conversion. So the K value is unknown. We are going to calculate 1 minus 0.8. So from these K values are 2.8. This K value is a CSTR K value. So this is taken as K2. K2 is equal to 2.8. But our objective, we are going to calculate the activation energy. We have the two reactor K value. Generally Arrhenius equation, this is assumption is given. K is equal to K naught into e power minus e by RT. So the first condition, P for K1 is equal to K naught into e power minus E1 by RT1. For CSTR, K2 is equal to K naught into e power minus E2 by RT2. So divide these two expression, K1 by K2 is equal to K naught are cancelled na, common term. Rest of the term e power minus E1 by RT1 divided by minus E2 by RT2. So this e power minus E2 by RT2 comes to numerator part. Numerator side means this minus comes to plus, is right. E power minus E1 by RT1 plus E2 by RT2. So here we want activation energy na. What do you do here? This side exponential form. So remove the exponential term, take ln both side. So the ln of K1 by K2 is equal to minus E1 by RT1 plus E2 by RT2. So in this case K1, K2 values are known. R and T1, T2s are known. Substitute all these values here. So ln of 1.209 divided by 2.8. So here E1 and E2. So both equal to E. Are you clear? So capital E is equal to E1 plus E2. Okay. So take E1 plus E2 is equal to E. E1 plus this is E2. R is a common term na. So R is given 8.314 minus E by 8.314, take outside. So E1 plus E2 is a E. So the minus E by 8.314 into 1 by 400. So this is T1 value minus 1 by 425. This is T2 value. Substitute all this data here. LHS side minus 0.834 is equal to minus 1.76 into 10 to the power of minus 5 E. So from this capital E is equal to 47,386. This is joule per mole. We want kilojoule per mole. So E values are 47.39 kilojoule per mole. So answer range is given 47 to 49. Our answer within this range. Okay. So our answer this is 47.39. This is within this range. So for further related videos, you can like, share and subscribe my channel. Thank you.